Thanks everybody for joining today. We have two special guests from across the ocean who are giving up some of their Friday night to give us a good talk today. Claudio and Fabio, who are from GARR and also representing some aspects of the GÉANT projects. And they are going to be talking a little bit about a project and a deployment that's working right now on GÉANT called Timemap. And it's going to focus a little bit on efforts to measure latency and jitter. And they promised that they won't do the talk in Italian, but we'll see what happens. So I will throw it over to you, Claudio and Fabio.
Good afternoon. No, it was a joke, but I was joking about zucchini before, but that's the only thing I'm probably going to say in Italian this evening. And then I stick to English for this evening or afternoon talk for you. So what we are going to talk about, let's just share my presentation with all of you. We are going to talk about a problem which has been for most of the time been underestimated, I believe, inside the networking people. And I am a network engineer, Fabio is also a network engineer, and so on. So Timemap is a tool that has been developed in the last 2 years inside GÉANT with other colleagues, of course, all over Europe, which is intended to measure and historically also trace the latency and the jitter which happens across the backbone. And we started to do it in a way that we don't do it into a laboratory, but we decided since the very beginning that we use the real GÉANT backbone as a whole as our laboratory, and we developed the tool over there and we test it over there and so on. So it might be look strange. Why do you want to measure these two little parameters that are on the network since ever and nobody takes care about? Well, I tried to make a road traffic comparison. So imagine that you turn on your radio, you're driving a car, and the report tells you that on Highway 101 there are 364 vehicles per minute. Is this something helpful for you? Is this something that tells you exactly what you are going to find in front of you on your way to destination? It may be that it is okay because you have a 6-lane highway like this one. And so, I mean, 364 vehicles per minute means quite a rare distribution of vehicles on the pipe. But it might also mean this. It doesn't tell you anything about the status of the traffic flow. It tells you only how many cars can go per minute on a segment of the road, of the track. And if this is the traffic flowing in a nice way like before, that's okay for most of the applications. But if there is a lot of stop and go, like in this case, you see all the brake lights are on because they stop every few seconds. Well, there are some sort of uses of the network which will have some very serious issue and will not let you do something at all. So in a case like this, it doesn't mean anything, any information like that. If you think of that kind of information in comparison to what we measure over normally the backbone of the network, that is the bandwidth measurement. You always can read how many gigabit per second you can have on a single segment of the backbone, but it doesn't tell you anything about the latency or anything about the jitter on that segment. It only tells you how big number of packets are going through and if you are close to saturation or not, but nothing else. So what normally you want to see when you drive a car is this. You want to know if there are delays, and of course you want to try to avoid any segment which is orange or even red. So you take a detour, you take a different path, or you know that if you really need to go there, well, expect some problems, and you have to wait. Also on the network, there are a number of applications which really needs to know the transit time and how the traffic is flowing. Is it just going in bunches and then stops and then another bunch, or very smoothly all the packets can go and timely arrive at destination? It makes a very, very big difference in terms of real-time applications. Anything which needs to control something from remote in real time cannot run if there is stop and go, and cannot run if there is a congestion or a traffic jam or an issue and so on. But until now, what do we have? Well, I just copy a little portion of the GARR weather map situation. Well, we only have the situation about traffic gigabit per second. If you look at this map, well, you will see, well, GARR is perfect, no issues at all. Everything is in the green area. Only a few links are darker green. So everything works perfectly everywhere, which is not the case. Because in some of these segments, if you measure latency and jitter, there are some issues. And you will never know by a weather map like this. So this was perfectly okay, as I said before. If you talk about bulk file transfer, for example, I am a physicist as well. So when I started to work in Geneva at CERN, and the issue there was to transfer the experimental data from tier 1 to tier 2 and beyond data processing center as fast as possible. But that was it. It doesn't matter if this stops and go and it takes a bit more than the expected time. Then you do processing offline. But this is not what we do with application of completely different type. These applications are the one, if you keep on the comparison with the car, which need to set the cruise control, and then you forget about the pedals. And you let the application go all the time by itself. You only maybe steer the steering wheel, but that's it. And the number of applications which need to set the cruise control is increasing very, very rapidly today, because the number of real-time things on the network are increasing quite a lot. And they're not only audio and video stuff, as I will show you. Just as an example, the project, it is called inside the GÉANT project, the LoLa monitoring, because it started from a very specific application, which is a video conferencing application, which is, his name is LoLa, but it means low latency. It is an application which needs really to have the lowest possible latency from end to end and the lowest possible jitter, because it normally uses about 1 gigabit of traffic for a full HD video stream and multi-channel audio system like 16 or 32 audio channels. It is an application which is in wide use in the music education world, also in the performing art one. And it is the one which allows you to just to play together at 300,000 miles distance without any issue, for example. Well, this is the map of the European installation on it. And if you see the red dots, they are the one which were installed in the last year. And it was an increase of 30%. There is exactly an equivalent one in North America. It is exactly the same. It is growing very, very fast. And of course, these users don't tell you that they are installing it. They just install it and run it. And of course, very often, the national results network, which are the one in Europe, which are equivalent to the regional networks in the US, very often don't even know what's going on, because they don't see the traffic. I mean, 1 gigabit of traffic is nothing for a backbone like GÉANT or national results networks. It may be something for a last mile, but not even for that is an issue. But for example, these are all the regional networks in Europe which are involved in having somebody running LoLa nearly every day, and it's practically most of them. The 3 one in red that were the last one which were added last month, for example. And what does it happen? Well, there are 3 locations, for example, one in Estonia, one in Italy, and one in Austria, which have just connected together, and they want to have a very little real-time round-trip time transfer, and they run about half a gigabit per second of traffic, and that's it. And they want to do it very, very smoothly. No network operation center will even realize this is happening, because normally it runs very smoothly. Well, this is the main principle of what I want to tell you, but don't think it is only something for audio and video. For example, there are people which do real-time control of equipment, or real-time control of experiment, or other things which really need to go down to, for example, robotic control, or for example, radio telescopes control, and so on. And all these applications exactly need the same measurement of latency and jitter to be sure that they work correctly. So we started to implement the service, and this is how the service was implemented in version 0. And I let to Fabio to comment about it, and then I will come back later on.
Thank you, Claudio. Good afternoon, everyone. So when we started designing Timemap, our first thought was having a tool that implements the typical extract, transform, and load pattern, having essentially three main blocks, focusing on microservice design for the whole service. First of all, we wanted to have a block that takes care of collecting data from the devices. Working directly on the GÉANT backbone, our speaking languages were Juniper real-time performance monitoring on one side, and TWAMP standard, emerging standard on the other side. And we wanted that the collecting module takes care of doing normalization, first stage filtering of the data. Then, of course, the natural choice was using a time series database to keep track of the data over time. And then, quite naturally, we decided to go for a visualization tool that allows us to show the different time series of the various metrics that we collect, and show an overall view of the data through a weather map. Next slide, please. Our first prototype was based on Elasticsearch and Kibana as main building blocks for the time series database and the visualization tool, respectively. And we inherited somehow some Python scripts that took care of querying the devices and normalize and store the data into Elasticsearch. The very first implementation was quite good enough. The software footprint for the input collection was not very large, was easily tunable. And we went on for about 1 year of data collection with no major issues. Please, Claudio, go to the next slide. So in this slide, there are two screenshots showing the original weather map that welcomed the user on the landing page. And then we had this time series visualization that essentially were just the Kibana dashboard that user can summon from interactive menu on the weather map. As I said, after a year of running this prototype, we started facing some issues related mainly to the limit of the open source version of Elasticsearch. Also, Elasticsearch is mainly dedicated to log analysis, so using it as a time series database was not the best choice we made. So we decided to review the whole architecture, mainly because we wanted something that have a smaller footprint in terms of resource consumption, an even smaller footprint in terms of custom code. We want something that is 90% based on open source available tools, because our goal is not on the code itself for the tool, but is on the data and on the analysis of the data that are collected from the GÉANT backbone. So we underwent to a complete refactoring for the service. Please, Claudio, next slide. And as the architecture was based on a microservice pattern, it was quite easy to re-implement the different building blocks by keeping the information flows the same. So instead of the custom Python script, we adopted Telegraph, and we used some small Python plugins that take care of querying again the devices and normalize the data that are now written into an influx version 2 database that again is queried by a visualization tool, and this time we used Grafana. And on top of everything, there is an HTML pages with some JavaScript and Shibboleth authentication, plus some authorization features that provide the user the familiar weather map that our users started to know. Everything is packed as Docker containers. So essentially, we have a central data lake facility that is implemented through Docker Compose infrastructure as a code. And this is where the data are collected and are stored. And then we have a couple of probes running Telegraph. One that takes care of using TWPing. Essentially, this is a personal machine with a Telegraph installed on it that queries the routers using TWAMP protocol. And then we have another machine that runs another instance of Telegraph that takes care of collecting data from Juniper real-time monitoring from SNMP packages. Please, Claudio, next slide. So, version 1 has many new features, as I said, beside the more efficient usage of the available resources. And notably, what we introduced is a richer authorization model. So we are now able, through tokens exchange and RBAC, to fine-tune the way that different probes, also third-party, could write data into the data lake. And also we can define different profiles, different roles, so that different classes of user can query different kind of information from the system. This is the main new feature from version 1, beside the different implementation tools. As I said, of course, our goal is not the code or the tool itself, but we want to understand data and what happens behind the data we see. So what's going on the backbone. Next slide, please. Claudio, do you want to
Yes,
go on?
I can add something. Well, I can start a bit from the previous slide on a second, from this one. As you can notice, there is still a dichotomy in the data acquisition part of the service, because we use TWAMP, which is a standard protocol, which it's going to be implemented by all the vendors on all the routers and all the software it does monitoring. And that's the way forward, of course, because that's the standard implementation, that it's an IETF protocol. So everyone will have to implement it in the very same way. But still, we do collect the proprietary RPM data, which the Juniper OS is able to provide to the current state. And the reasoning for this is, of course, that TWAMP is very new, and in the Juniper earlier version, there were some issue. It was not working properly in some versioning. And while RPM is very stable and does work since many years. So given that we want to collect data anyhow, we keep this, let's say, dichotomy up and running. And so we collect half of the data from one protocol and half of the data from the other one. and then we try to compare them, of course. In the end of the story, of course, we will switch off RPM and keep only Timemap up and running. At the moment, Timemap is installed, as Fabio said, in a single. It's going to be more than one single machine, but on one polling station, which then polls every router along the network and collects all the data. So it's a sort of end-to-end measurement, while RPM is a segment by segment. So I can have a map segment by segment along the whole backbone that we are monitoring at all. We are in the process, together with GÉANT operation team, to install Timemap clients on every router. So we are able to use Timemap also for segment by segment measurement. And when we are confident that this is okay, we switch off RPM. And then we move to a very standard implementation for that. The main reasoning for this, of course, that as Fabio said, we are not interested into the code, but we want to have something which is able to run everywhere and on every kind of machine and every kind of backbone, independently from the kind of machine and operating system that they run in the routers. The other main difference from other monitoring system is that we talk directly to the devices. We talk to the routers. We don't install a probe like Persona does, for example, and then we talk to probes. We just talk directly to the machines. And that also avoid a big burden of maintenance, because I don't need to maintain anything else in the router. And the route is up and running, because otherwise I don't have a network running. So there were the two main reasons behind it. And now, how does it look like? Well, we just made a change to the dark mode, because just to make a difference, so people see that it is a different implementation. The interesting thing is that this map is automatically designed by the routing data that we collect automatically from the backbone itself. So we get the adjacency data from the machines, and automatically we build a map. Of course, well, we do some manual intervention when there is too much overlap of nodes too close to each other, but that's all. So we don't need to make any update. If there is a new link, it will pop up automatically, and we will see it. And if there is a new measurement, it will pop up automatically. How does it work? Well, as I said, we measure link segments and end-to-end to routers. So if I click on a link, maybe later on, if we have time, we try to make it live. I open a menu like the one that you see, where I can get parameters like latency, jitter, and standard deviation, and the full RPM suite that I can get from that link. While if I click on a router on the yellow dot, then I get the data which I get with the Timemap from our probe machine to that one. So I get an end-to-end measurement. So I have two different view of the network, which I can see at the very same time. What do I get out of it? Well, we collected a few examples. I can go back for a few seconds to the previous one, because in this one, here we are. On the bottom right, you see quite an interesting phenomenon, which was completely unknown before we started to do the measurement. If you look at the dark blue line, this is a circuit, and you can very clearly identify that there are periodic rerouting over the circuit, because the average latency changes, and it stays the same for days, and then it changes, and then it changes again. So it does mean that the company which is provisioning the circuit does internal rerouting without telling us. So it does mean that we don't have a fixed number for the latency and the jitter on that link, because it depends on the day. And if you run an application which is very sensitive to latency, then you might have an issue, of course, which is something which we identified before, but we are not able to understand the reasoning, and now we do. It's a circuit, and the operator does rerouting without telling anybody. So, other thing that you can see now, if you click on a link, well, you can quite evidently identify that there are periodic events. For example, here you can see the big spikes. Well, the big spikes are the maximum. The maximum always exaggerate the effect of something happening on the network. But you can see that the spike also exists in the average one. And these big spikes correspond with jitter and latency changes and so on. What does this mean? Well, there is some event happening when there is a spike like this. And the event might be of any kind of possible source. It might be, for example, just temporary routing. It might be that the router itself is doing something, is doing, for example, is updating BGP tables. And of course, is not able to respond as performant as it used to be before, and so on. Keep in mind that these are every 5-minute samples. We are still trying to tune the sample rate. For the moment, 5 minutes seems okay for what we want to investigate. But when we try to do more in deep analysis, we will lower the interval, probably go down to less than 1 minute, and so on. We need to tune this to understand something like this. Another example is this one, for example. You see that there are very, very high events when there are very high variances in the jitter itself. When there is such something like this, it means that your packet flow does not go very smooth. You have a stop and go, so empty, then a bunch, then empty, then a bunch. And of course, any real-time application will need a lot of buffering to be able to cope with it. And if you don't do buffering because you want to keep the latency low, then your application doesn't work and stops working. Even more interesting, we went to, of course, to have a look back to the circuit we like, the very unstable one which we saw before. And this is what we see with DWAMP, which we were not able to do it before. Okay, this is a very stable link. This is a link which is run by Fiber. I don't remember which one is one, maybe Fabio does. I think it's the Amsterdam-London or something like that.
Yeah, it's in that area.
Yeah, it's the Amsterdam-London. So a very stable Fiber one. But I let to Fabio to describe what happens on the Frankfurt to Tallinn one,
yes,
which
yes,
is this one.
Yes, this is why Timemap is useful when you want to have a look at what's going on the backbone, because when you do sessions with Lola, for example, you tune, you do some very fine tuning of your local network, and you ask help maybe for the support of your regional NOC in order to have the best latency and jitter for your session, for your performance. But if after some hours the long haul behaves this way, all the tunings you did essentially are blown away, because the backbone behaves in a completely unexpected way. So you need to have a tool that goes beyond the simple active monitoring and measurement of latency and jitter. You need a tool that is able to keep track of the evolution of these parameters over the time, also over quite long periods of time. Otherwise, you cannot get trend lines. And as Claudio said, this is a very stable, very problematic link, because trying to control latency over a link that ranges from 10 milliseconds up to 26 or 27 milliseconds is a really daunting task if you are going to tune your network for keeping latency and jitter under control.
Yeah, imagine that in this case, for example, you're just trying to do a music lesson, of course. And of course, you try to keep the latency as low as possible. I mean, the overall latency that Lola is able to deliver is 5 milliseconds. So 20 is 4 times higher than the application itself. So you cannot live with it. But you need to keep it stable. Of course, you can fine-tune the buffering that you add into the receiving side in order to cope some small variation of the latency and so on. But if you need to take care of a 15 milliseconds variation over a few hours. Either there is somebody which is monitoring constantly the time map and changing the buffering all the time, but then the teacher and the student will start to shout to you because, of course, they will feel different condition every time. And we made a series of studies with blind tests before in the past project and years. Remember that a trained musician, a professional musician, is able to tell you that there is a difference of about 5 milliseconds, and they never do it wrong. So they feel 5 milliseconds difference in latency. So if the difference is 20 or 15, they tell you nothing is wrong, nothing is working, and they stop doing the lesson and so on. Furthermore, try to imagine that you are trying to control a remote equipment like this, and for example, it's a robot. And no surgeon will ever dare to use from remote a chirurgical robot like this, because he is not able to control what he's doing, and so on. Or imagine you are pointing a telescope. You miss the pointing all of the time because the latency is continuously changing and so on. So this is really an issue. It of course tells you very clearly that backbone made by fibers under our control are much better than renting a circuit. But sometimes also they show us that there are some routers which have some strange issues, for example, and they don't behave correctly as well. So the thing that we are doing in this very moment, now that we have the data and we start to have the historic data as well, is trying to identify some sort of known behaviors that we see on the network. And instead of having somebody watching at the data, we try to have a machine which is watching the data and try to set automatic alarm system and so on. So for example, in a case like the one you see now, I expect that there is an automated alarm which tells you, guys, this circuit is unreliable, do something and have a look to it. Or if there is all of a sudden a burst in jitters, I have an alarm, and the network operation people will go and have a look what's happening on that machine, and so on. So this is essentially the current status. It is up and running. Everybody can access it. You need to authenticate to it, of course. You need to be able to use GANT to authenticate to it. And the reason why we made the authentication on it was quite stupid, but quite effective. During the development, I don't know why, but we had, I think, 5 data breach, which went into the database and mixed up the data and destroyed the data. Okay, I don't understand the reasoning for that, but of course, people doing hacking are strange, so I don't care. So now you need to authenticate to be able to go in. There are, of course, admin user guide and so on. Everything is on GitHub, so it's open source and public domain. The source code is as well open and so on. What we are going to do now that the prototype is up and running and working well on the GÉANT backbone are 2 things, essentially. First of all, we are moving the service to production. The group of developers, which is me, Fabio, and other 5 people, did the prototype, but now we hand it over to GÉANT operations team. So we are having quite a number of interaction with them, because we need to establish production machines level for the servers which are running the service, and we need to have very full documentation on how you keep it up and running. And so you make it a service, and we hand it over to them. And then we just remain the last resort help desk if we need, of course, to help somebody which has an issue, or there is a bug or something to fix. And this is the first part of it. The second part of it is, of course, that we are trying to help regional network, the national network in the different countries in Europe, to install a copy themselves. Because, of course, it's quite evident that if I monitor the backbone, I'm fine to most of the cases to understand if something is going wrong on the backbone, but users are end-to-end, of course. And so I need to extend it to the national regional networks, and possibly even to the last mile if I can. So we are also helping people to understand how they can install it and so on. And we have already 5 regional networks which are willing to do that. One called us this morning, say, are you ready? And said, no, not yet, wait for a second. But they want to install it locally and try to understand it. Of course, most of the ones which are most eager to start are the ones which are understanding that they have a lot of real-time usage over their networks. And so they need their network operation people to be able to respond when there is a call, say, I have an issue, something is wrong here, it doesn't work, and so on. But for the rest, we will see what happens. But this is the plan. I mean, to try to deploy in as many installations as possible, and cover the data storage as well. This does not mean that we have already decided which way we manage the data lake, because there are options, of course. It might be that we just create a single data lake, which is populated by all the different regional networks plus the backbone. It may mean that we just keep separate data lakes, but the monitoring data are available to everybody. It is a policy matter, not a technical matter to take this decision. In a multi-domain environment, probably the second option is much more easy to deploy than the first one, because of course of multi-domain management issues and so on. But this is not something which has got to do with technical stuff, but only with political stuff and how to make it happen. So I don't know if Fabio wants to add something to this. Otherwise, we can stop here for a while, and in case we can open the live service and start responding to questions.
I have no additional points, Claudio. Thank you.
Okay, so I stop sharing the slides.
All right, well, thank you both for going through that. So I'll ask everybody again, if there are any questions, certainly type them into the chat room. I'd say if you're willing, let's maybe try to do a live demonstration and show some of the things that you've seen recently.
Yeah, let me go live and open. You're not going to see, of course, the authentication period because I did it already. So let me share the live dashboard of Timemap, which is this one. Here we go. Let me move it a little bit so I see the old dashboard. So when you open it, of course, this is what you get. It's a very same thing as before. Of course, sometimes the topology has some issue. For example, there is an issue up here I think you see my mouse, up here in this Baltic country, which is, I think, Latvia. We don't understand why the routing data tells us that this router is an end node while it is in the mesh as any other router, but it is something we need to fix. But imagine that in this map, I want to see what's happening on any of the segment. Well, I just go on the segment, I click, and then I select what I want to see. For example, the first thing I want to see normally, I want to see the latency and see what's happening there. And this is what I normally get. As usual, the maximum peaks are just, it might be just one packet, which was very late in being delivered. So the top peaks in the orange one are not very significant unless they are in bars and so on. The important things are the green and blue ones, which are the one down here, and the average and the minimum one are very stable. This is a fiber link, of course, with very minimal issues and so on. So I can say that here I can tune very easily any real-time application because I exactly know how long is the interval that the packet is going to take before being delivered. Here I can also, of course, select the time window in a way that I can, for example, decide. I can select the range, or I can decide I want to see the last 7 days, for example. Let's see what I get. Then I need to refresh. There we go. So you see, I got a lot of peaks, of course, but I ignore the peaks. And but I look at the green and blue line, which are absolutely stable. And this is something which is very reliable for me. I mean, I can predict what's going to happen there. I can go back for months, and it's going to be exactly the very same. If I if I go to the link, which we know very well is unstable, which is this one, which is a circuit, not a fiber, and I ask again, tell me the latency, well, I start to see something which I don't like. As you can see, even if I ignore the fact that I have many high levels of maximum latency, which is much higher than the average, I can ignore them, okay, but it might be a single packet, but I cannot ignore the green one down here, which tells me that there is a lot of variation in the latency. And remember, this is every 5 minutes. And a lot of variation even in the average. Even the average is not stable. So this is not a circuit reliable as the fiber I was showing to you before. And if I close the latency and have a look to the jitter, it is here. Let's see what I get. Well, this is something that a real-time application will not like at all, because there is a lot of stop and goes in the packet delivery and so on, both positive and both negative. So if you need to tune the buffering window for your application, then you are in trouble. The other thing that we can have a look is the TW ping installation. So if I select a router, for example, I go to Frankfurt. Here, the only one enabled is TW ping, of course, because it's the only measurement we have implemented for the moment. I see the full dashboard, and I can see that the router in Frankfurt down here is quite stable. There are some peaks in the real time, in the RTT and in jitter, but the averages are okay in all. I remember that we also installed a personal machine which is exactly aside this router. So, but I don't remember where it is in the dashboard. Maybe Fabio does. So maybe
the one in Frankfurt, Claudio.
Yeah, the one in Frankfurt.
It's not shown in the dashboard because
yeah, sorry, it's not in the dashboard because it's a private test. Yeah.
Yes, exactly. Let's try this. Maybe you can look up for this personal machine, looking for Frankfurt in the destination field. On the
here.
No, just on the destination variable. If you click
okay. Yeah, I click on it and then I look Frankfurt and see what I
on the top-down menu. Claudio.
Yeah. Let's see. This is Frankfurt there. No, it's not in alphabetical order, of course.
No. Because these are all the loopbacks of the. Here it is.
Where?
PSNP GN.
There it is. It's a personal machine. Yeah.
Yes.
Okay. And I need to refresh.
Of course, some metrics are not available because the TW ping client on Persona does not provide reflection times.
So okay, now if I had two windows, two screens, I could compare the data which I get directly from the Juniper and the data I get from the Persona probe, which is just connected with a 1 meter cable to the router itself. And we did it already, and they are very similar. They're nearly one-to-one mapping, one to the other. So it does tell us that the TW ping client on the operating system works correctly in the way we expect. And that's it for what we can do it for the moment. What else? Well, I think we can just open to question and let people ask us whatever they want to know about what we are doing.
All right. Well, thanks for walking through that. Looks like some really interesting stuff. So we don't have any questions yet, but I'll put the call out to people to please ask anything that you'd like them to show. I have a couple that I just jotted down as we were doing this talk. Are there any plans to use the data that comes out of this and feeding it into intelligent applications that can take advantage of it? for example, some of the things that you noticed or noted that were latency dependent, would having that monitoring information be beneficial to applications?
Well, I think this is exactly the plan that we have for next year. As soon as we are ready to have enough data collected and understand some behaviors, then we can really feed some, let's say, artificial intelligence data analysis tools to try to understand if there are trends or features which we can't see easily, for example, by just looking at it, and try to understand where they come from, of course, because the goal is not only to say, oh, there is something strange, but to understand why it is strange and which is the cause, and fix the cause, of course, if it can be done. So yes, I know we're going to do it. This is mainly Fabio works, not my works, but maybe Fabio can have some more
yes,
clue.
Indeed, one of the most interesting thing to investigate is trying to identifying through well, by comparing different data sources and correlating events. That's it. That's interesting. That's interesting, mainly to understand how different routers propagate misbehavior from one to another. We know that this happens for sure with routing, but we still don't know how exactly this happens on latency and jitter.
Yeah, a typical example, an accident which happened about a month ago. We discovered by having a look to the time map that, for example, the BGP routing tables between two countries, two regions in Europe, were sending the traffic over commercial networks instead of over the GÉANT backbone. And the reasoning for that was, of course, that the jitter that we got on end-to-end between these two countries was absolutely incompatible from what we expect on a fiber link run by us, run by GÉANT. And so we were having a look and say between these two countries, the jitter was about 20 times higher than expected over a fiber. And that was just impossible. I mean, the two routers were okay, no faults, no problems, no interface flipping, nothing at all. And then, of course, we handed it over to network operation people and told them, well, it's something we can't understand here. What's wrong? And we completely forgot to make the most stupid thing that we could have done, which is a trace route. As soon as we did, we immediately understood that instead of going via GÉANT, we were going via Telia, end-to-end, between two endpoints over GÉANT. And that was just a stupid error on the BGP costs, which were injected somewhere in the backbone, which was affecting completely a big region of the net of the backbone itself. So you also have some very interesting side effect that you find out without knowing it.
Okay. So we had two questions that came in. The first was from Jorge. Do you have any plans to deploy programmable data plane switches in the GÉANT network? If yes, do you consider implementing, or have you considered implementing high resolution telemetry and collecting different variables?
Well, for sure, we want to implement high resolution telemetry because that's the next step that we want to do. That's the evolution of Timemap. Again, I leave it to Fabio on this.
Yes, there is another team in W6 in GÉANT 4 that is taking care of in-network telemetry. Also, both are using, if I remember correctly, both FPGAs and P4 devices. We are in contact with them and we are moving in parallel. And at a certain point, we will have a point of contact where we can merge the two activities, at least from as a partnership of technologies, not as working groups. Can I answer directly also the second question?
Sure. Let me read it out so that we have it for the recording. Is TWAMP implemented on the routing engine or on the line cards?
For what Juniper told us so far, the TWAMP protocol is managed by the routing engine, but of course the counters are from the line cards.
And this might be one of the issues that we need to study about, because when it is in the routing engine, of course, it is affected by the performances of the routing engine. And we want to investigate, for example, the maximum that you see in the graph might be caused by the fact that the TWAMP is implemented into the routing engine, and also RPM is implemented into the routing engine. So that's why maybe you noticed one of the parameters that we measure is response time, which has nothing to do with the network, but it's a response time by the routing engine, because we are trying to correlate what's happening in the routing engine, and if this is the cause of the peaks that we see.
Personally, I suspect the RPM module is the guilty for those spikes, but we do not have a router that runs just TWAMP, but not RPM. So we cannot check right now if, for sure, sampling data through TWAMP is way lighter and faster than passing through RPM and SNMP polling.
Yeah, and it's also much faster to do the polling. I mean, one of the limits that an architecture like this over a big backbone like GÉANT is, of course, the time you take to collect all the data before you start it again. Because you don't need to forget that it takes time to collect the information for 10th of routers. I think they are 47 or 48 router at the moment. And in a round robin, we need to ping them all to get the data. So if I increase the sampling, then I will have an issue, of course, of the time that it takes.
Yeah, indeed, one of the very first things that we did is getting rid of the round robin all over the routers and having something that takes care of parallelize the sampling. So all the samples or the sampling process are done in parallel, and the samples are got in parallel also.
All right. Well, thank you both. I think that's it for the questions. So I'll put out a last call in case anybody has anything else. We'll make sure to get this posted, and the slides are already in the usual location as well. So thank you again for giving up some of your Friday night for this talk. We really appreciate you coming in and talking about this.
Well, you're welcome. Of course, when I said we try to deploy it on the regional network in Europe, doesn't say that it cannot be deployed anywhere else. I mean, so if anybody who is willing to give it a try, just contact us, and then we help you in deploying a proof of a concept or whatever you want, even on other networks. So it's not an issue at all. I mean, it is not copyrighted, not at all. I mean, it's a free collaboration by anybody.
Okay, I'll make sure I put that in the mail that we send out to people. Thank you both again. For people who are still listening, the talk next week is going to be from the University of Michigan team, and they're going to be talking about their experiences with their NetBasilisk security project. This is a follow-up to a talk they gave last year, I believe. So thanks again. Hope everybody has a good weekend, and we'll talk to you next week.
Bye to everybody.
Bye.